think about, I'll just jump into it. So looking at this, I have a graph. I want to do one that we can kind of look at it evenly. So I chose two semicircles. Those are the same size semicircles. So if I just want to talk about some ways that we can evaluate the integral from this one. For example, if I say what is the integral from 0 to 8, I'm going to call this function g of x, just for the sake of discussion. The integral from 0 to 8 of g of x with respect to dx. That means, again, what is the area under the curve between the graph and the x-axis from 0 to 8. I have a semicircle. The radius is 4, so it's half a circle. Pi r squared. I'm going to simplify that, and we see that the area is 8 pi. First main fact that we have when it comes to area is that area above the x-axis is going to be considered to be positive area, whereas area below the x-axis is going to be considered negative. There's lots of reasons why. The short answer is we know that when we're approximating areas, we do Riemann sums, so we're drawing in rectangles. And we know when we draw in rectangles, that y-coordinate is giving us the height. Well, if it's below the x-axis, it's kind of like having a negative height. So if I said what was the integral from 8 to 16, so it's the same sized semicircle, but since it's below the x-axis, it's going to be a negative value. Where this is important and why I like defining the definite integral as the net area and not the total area, if I expand this and ask the question, what is the integral from 0 to 16 of g of x? What do you think the integral from 0 to 16 of g of x is going to be? 0. So those areas out, so that first semicircle had an area of 8 pi. That second semicircle, technically an area of negative 8. Overall, the net area is 0. That's another big idea when it comes to the definite integral. The last other kind of big idea that comes to evaluating a definite integral geometrically. So we know that area above the x-axis is positive. We're going to add one disclaimer to that, as long as you're moving in a forwards direction. So if I say the area from 0 to 8, the area from 0 to 8 is 8 pi. But if I change it up and I say what is the area from 8 to 0, it's kind of like you're finding the area but you're moving backwards. So that's going to change the sign of the area that you're using. So positive areas become negative, negative areas will become positive when the limits of integration have an area of negative 8 pi. Questions on that as we start kind of pulling some of these pieces together? All right, so then the first piece I want to pull together, you do need to kind of understand where the Riemann sums come into play for this. Before we look at the Riemann sums, I do want to give us the first fundamental theorem of calculus. I put it in brackets in here because sometimes it's just plainly called the fundamental theorem of calculus, but there is going to be a second fundamental theorem of calculus, so I like making a distinction between the two. And the first fundamental theorem of calculus, you first might ask yourself, well, why are we learning something called the first fundamental in November? It's the first fundamental theorem of integral calculus, to be even more clear. And what it states is it gives a way to evaluate a definite integral. We know that most functions, when you graph them, they don't create nice geometric formulas. You can't graph a quadratic and draw a perfect triangle underneath it because of the curves to it. So the way that we evaluate an integral, for a definite integral, same thing we're doing yesterday, you still have to find the antiderivative. But for definite integrals, we don't need to worry about the plus c. So you're going to find the antiderivative first. You're going to use a vertical bar to represent you haven't evaluated it yet, and you're just going to carry over those limits of integration, whatever they may be. And then big idea, to evaluate a definite integral, you're going to plug in the top number into your antiderivative, then plug in the bottom number into your antiderivative. And that's why you don't need the plus c, because technically it's that first antiderivative will have a plus c, minus that second equivalent antiderivative with plus c, you end up subtracting them out. There is one thing that must be true for you to use the first fundamental theorem of calculus, and that function you're integrating, f of x, must be continuous on the interval from a to b, with brackets on it. If you have like asymptotes, then you might have to like split it up into two intervals. But we will learn some BC only topics, some topics that are not in AB, of how to evaluate integrals that go across like asymptotes and discontinuities and things like that. So some other ways that we can think about the integral and how we evaluate it. So sometimes I think students mess up like thinking about the antiderivative. So another way we can rewrite the first fundamental theorem is like if I integrate from a to b of g prime. Well, what's going to be the integral of g prime? G. So then we think, okay, so the integral of g prime would be g. Still haven't evaluated. How do we evaluate integrals? You plug in the top number minus you plug in the bottom number. And this is what's going to lead to a whole bunch of applications. We won't really get into them until second semester. I put this green box on here. I don't know if you remember when we first learned PBA, we did an example with like a bug, but that's where this is connecting to. And basically what we can connect this to is anything that we can find an antiderivative of can often have some sort of meaning when we do the context. I don't want to like stress this out with the context. Again, this unit, I just want to focus on the skills. But if I think about the integral of velocity, for example, that was the example we did when we first learned PBA. And I was integrating velocity from between two numbers. What would the integral of velocity be? Position. And so I know that if I'm integrating velocity from A to B, this would be equal to the integral of velocity's position, plugging in the top number, minus plugging in the bottom number. Well, if you think about what's in physics, if I have like some end location minus the start location, this is just the same thing as displacement. So like we'll see a lot of connections between what happens when we integrate that does create this subtraction. But for now, we are just going to look at like how do we find it and just be good with that. And we'll add the applications after Thanksgiving, but mostly second semester. So as an example, or excuse me, before the example, there is one important thing we need to make sure we do. So the AP exam does want you to understand this concept. So we started out this week talking about Riemann sums. And with Riemann sums, we had like LRAM, RRAM, LRAM, TSAM, and those were all used to approximate the area under the curve. We now know that the integral is the exact area under the curve. And you do need to kind of understand the link between those and why it works the way it does. So like if I just start drawing in a Riemann sum, I'm just going to do an LRAM for the sake of my diagram. We learned Monday that we could find a bunch of rectangles. We could find the area of those rectangles, add them all together, and that would approximate the area under the curve. It's not exact, because obviously like sometimes it's over, sometimes it's under, but it would give us an approximation of that area. What are some things we could do to be more accurate? How can we find a more exact approximation if we're just still talking about doing a Riemann sum? You can do more rectangles. Like the smaller those rectangles are, the more of them you have. The more rectangles you have, the more closely it's going to follow that curve. So where the integral is coming from, and this is like bare bones explanation of where it's coming from. We know that when we did Riemann sums, we were basically adding up the areas of rectangles. Well, what was the area formula we used for rectangles? Base times height. So I have the height times the base, and we know that we're just adding up a bunch of rectangles. In math, we have a symbol. You might remember it from the summer work. What symbol do we use for adding up a bunch of things in math? Sigma. So basically, this is like not a pretty version of it, but Riemann sums can be thought of as like the sum, that's sigma, the sum of a bunch of rectangles. Sigma is the Greek letter for S, so I'm going to draw the letter S. There's the letter S, stretched out. When we did those rectangles, what variable was associated with the height? Variable in the coordinate plane. y. So instead of writing y, what can we call y instead? F of x. How do we find the size of the base of your rectangles? Delta x. So delta x is used when we have like a, this x minus the other x. If I want to talk about a really, really, really small, infinitely sized change in x, what would I say instead? Delta is the Greek letter for d, so I would just say dx. And that's literally where it comes from. There's some limits there, like basically we're saying like the limit as delta x is going to 0, and that's where that's coming from. But literally, an integral is you adding up an infinite number of rectangles with an infinitely small width, and the height's just the y-coordinate. And actually, if you were a student back in 1700s, 1800s, you wouldn't always interpret that as an integral sign. Like that would be the letter S to you. The English alphabet back then had 2 letters for S, and often when they had 2 S's next to each other, one of them was written that way. Don't believe me, just go look up an image of like the Constitution and see how they spell Congress. One of the S's in Congress will be spelled with that S. But that's where the integral comes from. What's more important though is how we actually evaluate them. So I just have 2 examples because honestly it's just like what we did yesterday, but after you find the antiderivative, you just have to plug in the top minus the plugging in the bottom. So looking at this integral problem, again, we know this is a definite integral because I have numbers on my integration sign. The bottom one's called the lower limit of integration. The upper one's called the upper limit of integration. When I see that, you don't have to have the graph in front of you, but this is the integral from -1 to 2 of some function. I graphed it here. The answer to this is literally the area from -1 to 2. So like if I just kind of draw that out, -1 to 2, like you can see that this is definitely not like a geometry formula you know at all. Like there's like a flat side, there's a curved side, like we don't have a formula for that. When it comes to showing your work for a definite integral, you first want to show your antiderivative first. Just like the derivative, you can't plug anything in until you find the derivative. You can't plug in anything until you find the antiderivative. So what's the antiderivative of 3x squared? X cubed. The derivative of what gave me 4x? 2x squared. The derivative of the integral of 2 is 2x. We want to show we haven't evaluated it yet, so I use that vertical bar. We will always plug 2 numbers into our definite integrals, and then for our final answer, simplify it if you want, but make sure you use parentheses correctly. Plug in the top number minus plugging in the bottom number. So I have 2 cubed is 8 minus 2 times 4, 8 plus 4 minus -1. -1 cubed, -1 minus 2. And again, that number, whatever it is, represents the area under that curve. Should that area be a positive or negative number? Positive. This whole area is above the x-axis and we're moving forwards, so it would be a positive area. Try the second one for me. So secant squared does have asymptotes, but I'm integrating it between the asymptotes, so we're good to go. But again, just find the antiderivative, same thing we did yesterday, and then plug in the top number minus the bottom number. Make sure you evaluate trig in your problem. And again, don't try to do any like weird power rules or chain rules. Just think to yourself the derivative of something is secant squared, and that's what your antiderivative is going to be. So there's my work. Again, these shouldn't be difficult when you're evaluating. So what is the antiderivative of secant squared? Tangent. And then plug in the top number. Tangent of pi over 3 is square root of 3 minus the tangent of negative pi over 4. Fourth quadrant, so that would be a -1. And that's where the +1 is coming from. I can see that the area is all above the x-axis, and I'm moving forward, so it makes sense that root 3 plus 1 would be a positive area. Hopefully you can kind of imagine, like, at least the ability this gives you to find the area of things that aren't traditional shapes. But that's going to be like our main concept of what we're going to interpret the definite integral as being. Last thing I want to finish with is just to kind of make sure we understand its meaning. Is this thing called integral arithmetic. This is also a very common type of AP question, just to make sure students understand what the definite integral is and what that definite integral represents. And so I've given you some information. I say, hey, we know the integral from 0 to 2 is 5. I also am telling you that the integral from 0 to 6 is 4. And you can use that given information to find the remaining 4 of these. And you just think like 0 to 2 just means like the area, and I do want to be more clear, the net area from 0 to 2 is 5. And then from 0 to 6, its net area would be 4. So go ahead and try the remaining 4 of those. You can think some of these through like geometrically, think like what transformations might be happening to the shape. But see what you can do with those 4 problems based off of just that given information. And this is where we're going to wrap up today's notes. If you're looking for an easy one to do, I think the second and third one are the easiest ones. The one that students most commonly miss when I assess this is an example of like the very last one. So looking at that first one, my thinking about that one is we want to find the definite integral from 2 to 6. So we want to find the area, the net area under the curve from 2 to 6. If I know the area overall from 0 to 6 is 4, and from 0 to 2 is 5, what would the area from 2 to 6 have to be to make the net area 4? -1. So that's why it's important to make sure we remember that the definite integral is net area, because any negative area is going to take away like the accumulation of area that you have. This next one, if I have the integral from 6 to 0 of f of x, those limits of integration are in reverse. So what is the definite integral from 6 to 0 of f of x going to be? It's going to be -4. So from 0 to 6, it's 4. So from 6 to 0, it would be -4. Looking at that third one, we have the definite integral of 3 times f of x. Thinking about just like transformations, if I multiply a function by 3 in front, what's happening to the graph of that function? It's stretched. It's being stretched by 3. Well, if I stretch a function by 3, what's changing to the area under the graph? Also stretching by 3. We also know, if you just think about like how derivatives work, coefficients can kind of just carry across. Same thing works for integrals and antiderivatives. So for that one, you should have gotten the 3 times the 5, which would have given you 15. And then for that last one, we have the integral of 3 plus f of x. How many of you got 8 for that one? Oh, good. So maybe we're all correct. 2 ways of thinking about that one. Because the answer is not 8. Most people want to see a 3 and just add it to the integral from 0 to 2. 2 ways to think about that one. The way that I tend to do it, again, me being more of just like an algebra-minded person, I like splitting that up with just like 2 separate integrals. So we know that with derivatives, you can integrate each term separately. Same thing also works for integrals. So you could think of this problem as the integral from 0 to 2 of 3 dx plus the integral from 0 to 2 of f of x dx. We already know that the integral from 0 to 2 of f of x is 5. We now know how to integrate 3. What's the antiderivative of 3? 3x. And then we still need to evaluate it, plugging in the top number minus plugging in the bottom number. You should get 6 plus 5 for an answer of 11. I do think it's important to remind ourselves like why it's 11, because like a lot of times students, they know the first fundamental theorem calculus, it works, but you lose like the context of the meaning of it. So like I don't know what the graph of f looks like, so I'm just going to make something up. And if I just make something up from 0 to 2, again, I'm just making it up. Clearly, this won't be like a correct graph. But there is f of x. We know that the area from 0 to 2 is 5. Conceptually, to think about what's happening, when I added 3 to f of x, what was happening to that graph of f of x? Shifts up. When we shift something up, it means that everything is shifting up by 3. So like this is going to go up by 3. This will also go up by 3. So there is the new f of x plus 3. So the idea behind this one and why we can get the same answer, so we shifted it up. So like there's the original area of 5. I'm going to try to color code it. There's the area of 5, but underneath this shifted up by 3, we now have this box of extra area underneath it. What's the area of that extra box that is now underneath that function? 6. So you can't see that. The base of it's just a rectangle of 2. And we shifted it up by 3. 3 times 2 is 6, and that's what we saw show up when we did the integral. So kind of 2 ways to think about that one. Again, I wanted to make sure we keep that connection that definite integrals do represent an accumulation of net area. So that's where I'm going to wrap up my notes for today. The to-do list and kind of talking about the quiz. Quiz is on Friday. Tomorrow is mostly going to be a work day. I do have like a warm-up just to kind of tie up some loose ends of the 2 slides I didn't get to yesterday and today. The quiz is going to mainly focus on Riemann sums, which when I say Riemann sums, there's 2 things you need to know about them: how to find them, the 4 types, and then also how to determine whether it's an underestimation or an overestimation. And then indefinite integrals, so just like finding the antiderivatives, having plus c on your answer. The very back of the last page will have some definite integrals on it, but as long as you know the main gist of what a definite integral is, you should be fine. So all I'm really saying is like on Friday, at a minimum, you need to have homework 1 and homework 2 done. I recommend also completing homework 3, but if you have a lot going on, then at least maybe do like a few of homework 3, and you can just save the rest of homework 3 for next week. Looking ahead, we only have 1 more topic to cover in this unit. We'll do that on Monday, carry over a little bit into Tuesday, and then we'll test on this unit at the end of the week. And then after Thanksgiving, we start getting to do the fun integrals that aren't so straightforward. So y'all go ahead and get started with that. Let me know which questions you have, and I'm more than happy to help and answer your questions.